right edge, and it moves toward the left until it finds an element that is smaller than the pivot, which is 6. So it stopped at 2. Okay, this is J. So at this point, this element is bigger than 6. This element is smaller than 6, right? So what happens is that we are going to do a swap. Okay, do a swap. So the swapping will make this one make this one 2. And it's going to move 10 to here, right? Right? So because this element is already smaller than 6, so we move on. Okay, and now I is pointing to 13. So 13 is bigger than 6. J, okay, well 10 is bigger than 6, so we move on to the right. And again, we stop here. Because, 3 is smaller than 6. So again, we do a swap. So we move 3 to here, and 13 to here. Okay? And then I move, because 3 obviously is smaller than 6, so it's good. So I move, further. Now we do the 5, right? And then we move I to 8. So 8 is greater than 6. So that's I. And then J move to the left, right? Because 13 is already bigger than 6. So we move J to 8. Well, 8 is bigger than 6. So we move to J to pointing to here. But now IJ somehow change past each other, right? Okay, in this case, we know we already put smaller elements here, larger elements here. So at this point, okay, it's safe to again do a swap between the last element in here, okay, with this one. Okay, either you do this or you swap 6 with 8. No, you cannot do that. Yeah, so 6 is fine. 6 is fine. So this one becomes 6. This one becomes 5. So now we are done. Okay, this is a pivot. This is a pivot, and we already break. Okay, these numbers into 2 parts. The first part has numbers smaller than the pivot. The second part has numbers greater than the pivot. Okay, and this is similar to what we did previously. For I and J, but in the sense that in the new version, or the version that's stated in the textbook, basically both I and J grow from the left hand side. Okay, but in this version, I and J have start from 2 different opposite locations and moving toward each other. But the basic idea is the same. Okay, because there are some swapping that is necessary. That's the first thing. The second thing is that both of them takes linear time to finish this partition. Okay, so either this approach or the approach I mentioned here. Okay. Theoretically speaking, they are both quicksort. Okay, the only difference is that the partition, this partition function is implemented slightly different, but the time complexity remains the same because this part takes linear time, regardless of which version you are using. Okay, I believe like this version is mentioned in as an exercise in the textbook. Okay, as I said, like in some other textbook, this is like the one that is discussed as the quicksort. And it's like when I first learned quicksort, it's this version. Okay, but you can see that I mean, both versions have similar concept. Okay, similar concept, and it's similar results. Similar results. Okay, so back to the quicksort. Okay, we are in a position to talk about its time complexity. Okay, so in this analysis, okay, we could assume all elements, all input elements are distinct. They are different. Okay, all elements are different because like if some elements are the same, I mean, you can just treat them as like change like some condition input from the smaller than to smaller or equal. I mean, supposedly it doesn't change the complexity. Okay, so to make our discussion easier, okay, we can make such an assumption. Okay, so in practice, there are better partitioning algorithms for when duplicate input element may exist. Okay, yes. Okay, actually, there is exercise. Okay, in the home in the textbook that talks about this. You could try to think like why if there are many duplicates like helps I mean to do the partitioning. Okay, in other words, I mean because you can see that okay the complexity actually most of the time happen. I mean for the quicksort is spent on the partition like a procedure code. So if it doesn't take that much time, okay, if you have a better partitioning algorithm out there, I mean obviously like it's going to improve the performance of your quicksort, okay. But regardless, okay, that Tn okay to be the worst case running time on real n elements. Okay, let's assume this is complexity. Okay, the worst case running time, worst case complexity is T of n. Okay, with n element. So the input, if it's sorted or the reverse is sorted, okay, that would be the worst case for the quicksort. Okay. Okay, let's think about this. If it's in the reverse order, okay, let's consider like the reverse order and the version of the quicksort that we mentioned here. I mean this partition. Because we start from, like ij start from two different ends, right? And if you are going to find, like, you need to do the swapping all the time if it's in reverse order, right? Right? Okay. So that's the first thing. The second thing, why is like, I mean, if it's in reverse order, it seems that, I mean, you need more time for partitioning. But the actual problem is not about partitioning algorithm. It is about the pivot. Okay. If say like if it's sorted, if the array is sorted, so this element is going to be the smallest one, right? Okay. So you could imagine, after you run the partition, okay, the first part which contains the elements smaller than the pivot, contain zero element, right? There will be no element that is smaller than pivot, right? And all the other elements are bigger than pivot, right? Okay. So in other words, it's going to be if original the time complex is here, because you are going to call this recursive. So you will find that it's going to be like this. This is the cost for you to run the partition procedure. But suppose originally you partition your numbers into two parts. You hope these two parts have roughly equal size, right? But unfortunately, it becomes like you can only exclude the pivot. All the other n-1 elements, they are all bigger than your pivot, right? So it becomes something like this. And then for the similar reason, okay, when you run the quicksort, recursively, from the second element to the last, okay, obviously the second element is going to be the smallest element for this rest of the n-1 elements, right? So it's going to be, again, this part is going to be T n-2 plus, let me just write it like C times n. Let me just write it as C times n. So this will be C times n-1 plus C times n. Right? Okay, so you keep doing that. If you look at, eventually it will be T1, okay, plus, C times 2 plus C times 3 plus plus C times n. Right? Right? So this obviously is n squared complexity, right? So this is even when the numbers are in ascending order. If the numbers are in descending order, it doesn't change the fact that each partition will give you, one part zero element, the other part like all the other elements. OK， 就是说，如果说你是排，就是从小到大，那你每次 partition， 你就会发觉说每一个是没有 element， 另外一个剩下所有都在那边。那这个不管是你是从小排到大的，或从大排到小，都有这个问题。Okay, so it is really not about the number of swapping. It is about this. Okay, so that's like what I meant. I mean like the worst case is the input elements that are already sorted or in the reverse sorted, okay, or either in ascending order or in descending order. Okay, so if you are doing the partition around the mean or max element, that's the worst case. That's the worst case. So because one side of partition always has no element, okay, that's the reason why we have this. So the kind complexity becomes something like this. So I don't need to go into detail. You know this is like n squared, like high complexity. This is obviously arithmetic series. 这是等差数列，对，等差数列大家知道怎么加。So if you want to use a recursion tree to take a look, it's going to be, you can break it like T0 plus Tn minus 1 plus Cn, and T0 will stop. It's going to be a constant cost. This one, you can further broken it into Cn minus 1, T0, Tn minus 2. And you keep doing that, okay, until you get like a constant cost, okay, which is usually T1. Okay, so you can just do a summation here. Okay, and all these T0, okay, well, assuming they have the similar constant cost, the result is going to be, you need to add up all the costs from the leaf node as well as the intermediate, as well as the internal nodes. Okay, so it's going to be, okay, this internal nodes add up to be like something like this, which give you n squared time complexity, and all these leaf nodes add up to be, because you have like a linear amount of linear leaf nodes, so it's going to be theta n, okay, and because like you have theta n squared, where you get from here, so obviously this term gets absorbed into here, so it's going to be theta n squared. So that's like if you use like a recursion tree to analyze it, you are going to get the same result, obviously. So, let's say if we are, lucky, okay, then, okay, let's assume the partition always splits the array into two equally sized groups. Okay, this is like when we are very lucky. So it's going to be T of n equal to 2 times T of n minus n divided by 2 plus linear time for partition, right? So based on the this is actually exactly the same. This recursive formula is exactly the same as the merge sort, right? So because the merge sort we know is n log n, so this one obviously is also theta n log n. Okay, you can check out like master theorem, okay, or you can try to use a recursion tree. Basically, they'll all give you n log n. Okay, so this is when we are very lucky. But remember, I told you like when we talk about this analysis, algorithm analysis, I told you earlier that it is useless usually to talk about best case scenarios, right? 通常我们在讨论演算法的复杂度的时候，我们是通常不考虑所谓的 best case scenario 去做分析的，因为这样的分析通常是没有意义的。OK， 因为这样的事情不太可能发生，或者说这是特例。OK， 所以我们讨论演算法，跟你们讲，通常只有2种可能去讨论演算法是复杂度，一个是什么？一个是就是前面讲的 worst case， 我们已经知道这个 quicksort 的 worst case complexity 是 n square，n square 当然是不好，就跟 insertion sort 一样。insertion sort 我们认为是我们叫它 elementary sorting algorithm， 就算是我那时候跟大家讲说 insertion sort perform well when you don't have so many elements， 你就有10几个 element， 那 insertion sort 还就很快，那实作也非常快，所以并不是说 elementary sorting algorithm 就一定坏，这要看你的实际应用情况。但是基本上我们讨论所谓的 elementary sorting algorithm， 就是至少是 n log n 的。有没有更好的？我们后面再讲。有更好的，但是更好的有一些假设，但是先撇开这个不讲。
那你说，那为什么我们叫这玩意叫 quicksort？quicksort 什么时间复杂度那个最快时间复杂度是 n 平方？哦，我还没讲完，就是说我们一个是讲说，就是我们分析演算法的复杂度，一个是 worst case 分析，另外一个是什么？就是 average case 分析，就是你的时间复杂度的这个期望值。OK， 我们有时候我们在做这个演算法的那个要怎么讲，就是它的，我们可以分析它的期望值，就是 based on 它的那个分布啊，或者说整个的那个各式各样的所有的可能性，把它这个结果作为平均之类的，那得到它的期望值。那这个的话，你说这个 best case 当然是没有什么意义 ，it's useless to talk about the best case scenario. However, this is, as I said, this is just for intuition only. Okay, we just try to get intuition. So what if the split, okay, always give us like a, 1 to 9，就是每次我们做这个 partition 哦，这个两个 group 哦，它的那个 ratio， 它们的比例哦，是1:9，1:9蛮烂的吧？对不对？1:9应该是看起来已经不太好，对不对？就是我们保证一个很烂的一个 ratio，1:9，那就是一个是1/10，一个是9，所以 T of n 就变成 T，OK， 1/10 n plus T 9/10 n plus theta n, right? So this will be the recursive formula for case like this. Okay, so what is the solution to this recurrence? Obviously, the master method doesn't apply here. Okay, 就是那个 master 因为这不是那个 format 就不是这样子。However, we could still use like the recursion tree to get an intuition how bad it is. Okay, so let's try to use the recursion tree to take a look at this almost fast, or you can say it's a pretty bad way, because every partition is like 1 to 9. I mean, it's not that good, it's not that bad either. So it's going to be like this. In the first, division, and then we can keep doing that. Okay, we can keep doing that. Okay, and keep doing that. So obviously, this branch will be much shallow. 这个 branch 会比较短，对不对？ Because each time you go on the left hand side, your n is divided by 10, right? 每次你往左边走一格，它是不是被除以10？对不对？对不对？ And on the other hand, this branch will be the longest one, right? This branch will have been the longest one, because every time you go down one level, the branch, the number is going to be only divided by 10/9, right? 除以9/10啦，对不对？9/10，但9/10当然还是大于1啦，你还是变小的 ，OK？ But this reduction is much slower, right? It's much slower. So obviously, this branch, the leftmost branch is much shorter than the rightmost branch, right? 这边没有问题吧 ？OK， 那它到底高度多少？这边的高度就是 log 10除以9当这个 base 的 n， 这个还是一个 log， 但是这个 log 的 base 是这样子， 它是一个比较小的 base， 一个都比较大的 base， 比较小 base， 比一大，但是是一个比较接近一的 base。那另外一边，所以这边的这个 branch 比较长，这边的话这个 branch 比较短，所以这边是这个每一次除以10嘛，所以这边是 log 以10为底的 n 不见。You know idea， 这个是 log 以10为底。那 OK， 你如果去看这个 Cn， 这每一层，如果说你没有，你看你把它加起来1/10 Cn，OK， 你就 add up the same level，you know 1/10 Cn plus 9/10 Cn，OK， this is you get a Cn. This level obviously the root is Cn. This level is Cn. This is this n goes down to here. It should be here. Okay. It's 1/100 Cn plus 1/9. 9/100 Cn. This is 9/100 Cn. This is 81/100 Cn. If you add it up, you will be surprised to find that it is still Cn. So every level gives you Cn. And at the most, we have this many levels, right? Log, 10/9, and right, we have this many levels. So the worst case is, the best. I shouldn't say best case. I mean, whatever we have here, it's going to be this many levels times Cn, and in between, it's going to be greater than this one, and it's going to be smaller than this one. Okay, Cn times log 10/9, and right? 对不对？因为这边有一些项，这边有一些项是不见的，但是我们知道在这边的时候全部都还在，但是在这边的话很多都不在，但是没有关系，你这个是你的 lower bound， 这个是你的 upper bound， 你的实际的数字是在这个中间 ，right？ But both sides give you n log n, right? Both sides give you n log n. So obviously, okay, T of n is n log n. Okay, T of n is n log n. So even in this case, when it is the almost best case, or a pretty worst case, every time you do the partitioning, the ratio is 1:9. It's pretty bad. You still get a log. Okay, and then let's consider another scenario. Suppose we alternate lucky, unlucky, lucky, unlucky, blah 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 blah. So this is again, this is for intuition. This is for intuition. So when we are lucky, okay, Ln becomes 2 times Un divided by 2 plus theta n. So that's when we are lucky. But when we are unlucky, our Un, okay, becomes L, okay, because we come back to this initial situation. Ln divided minus 1 plus theta n. So this is it's kind of like这个 recurrence relation system， 就是递回这个函数组哦，递回函数组。那 if you want to solve this, okay, we can try to substitute. Okay, it becomes like this, and then what we get is something like here. And if you consider this one, okay, this minus 1 usually we can absorb it. Okay, so basically, okay, we are still able to use the master theorem to say this complex is n log n theta n log n. So Well, so if your partition every time give you like one ratio 1 to 9, it's n log n. If you alternate to have lucky and unlucky case, I mean your time complexity is still n log n. So, you know, it looks like this quicksort is unless like something very terrible happens. Otherwise, like it's really relatively easy for us to get like n log n complexity, right? So, but again, as I said, like all these are there just to help us to build intuition. Okay, so we are, I mean, we want to ensure that this is not the result of luck. We want this n log n to be more what should I say, certain. But when you analyze the complexity, okay, especially when you are doing like average case, average time complexity or expected time complexity, usually we talk about randomized algorithm, because for like a regular algorithm, it's deterministic. Okay, so it's we still could talk about expected time complexity or average time complexity for like a regular algorithm, but it's just like it would be based on the distribution of the input. Okay, so in order to avoid that, we usually try to randomize algorithm. Okay, so this is how we get things done. Okay, we try to make the quicksort a randomized algorithm. Okay, so the basic idea here, okay, we are going to partition the quicksort around a random element. Okay, when we say a random element, I mean like we are going to pick a random element as pivot. Okay, so first the running time is independent of the input order. Okay, because we introduce randomness into the picture. And second, we don't need to do any particular assumption, okay, about the input, the distribution, okay, because like again, because of randomness, and we have no specific input to elicit the worst case behavior. Okay, previous in the quicksort, the original version. I mean, we know like the sorted, if the input elements are sorted, either in a single ascending order or in descending order, both such case will give you like worst case, right? 就是排序好的，不管是上升排序或下降排序的那个 input， 在原始的 quicksort 都会给你最坏的情形。However, if you use the randomized quicksort, you randomly pick a pivot. Okay, I mean then there is no specific input. It's going to guarantee the worst case behavior. Okay, and the worst case is determined only by the output of the random number generator. Okay, so there are some benefit of doing so. Okay, so let's talk about this in more detail. Okay, after the break. Okay.
1到3思考就 对，那他还有写那个14个业数跟这个